to our astronomy seminar. We're very pleased to have Dr. Chris Fryer visiting us from Los Alamos National Lab. He can only tell us about certain things, and that's what he's going to tell us about today. Dr. Fryer did his graduate work at University of Arizona before, I've already forgotten. There's a postdoc in there in between, or did you go straight to Los Alamos?
Went to Santa Cruz after that.
Santa Cruz, that's right. You were with Santa Cruz, student with the venerable nuclear astrophysicist Stan Woosley before taking a job at Los Alamos National Lab, where he's been since working on, well, really the supernova engine. So without further ado, I'll turn the floor over to Chris to tell us about that.
So, and I guess I'll apologize for this talk before I even started. Los Alamos has these grants that you can do where it's internal money, it's a big amount of money, and you're supposed to synthesize things. So we did this proposal where we said, we're going to look at supernova, look at all the observations, we're going to do the theory behind all of them, which was an idiotic thing to say in the first place. And maybe the arrogance of theorists. But we said we would do this and put it all together in one picture. And at the end of the 3 years, we hadn't gotten near doing any of that, right? So they had given us all this money, and at the end of the 3 years, they said, give us a summary. How did you solve the big problem you were going to do? And I realized I hadn't done it. And so I thought I should at least put a review together and see what we knew from the core collapse engine perspective. Now, understand that from the core collapse engine perspective, the observations usually that we worry about is that somehow stars explode and we need to get that to work. We haven't worried about the details that much in the past, and most people that work on the engine don't worry about the details. I want to talk a little bit more about the details that we have in the past and show you how those details are starting to matter for the engine itself. So what I want to do is I have broken up into some, this is the apology part, it's lots of little pieces that I'm trying to tie together. So hopefully I'll bring you along with me as I bring in all these pieces. And we'll talk a little bit about the progenitor. The engine that I'm gonna focus on is this convective engine that most of the engine modelers are focused on right now. We'll look at explosion energies. We'll look at the trends with what trends the convective engine predicts for progenitor explosions with progenitor mass. We'll look at the pitfalls of using light curves by themselves. So where we found it was harder than we thought was to actually learn something about the engine from the supernova light curves. I'll talk about ejecta masses and ejecta distributions, and then compact remnants. And if I have time, I'll tell you one of the surprises we have with kicks onto these compact remnants after they're formed. So it's a lot of different information. Hopefully I can pull it all together, which I couldn't do for this video project that I was enjoying. So what is the supernova? Here's the classic one, supernova 1987A. It probably steered some people into the supernova field. I don't. How many people did it hurt your, take you out of a good cosmology field and into supernova? Who knows? But I'm looking at people that it might have affected in that way.
It's good to have data, actual data.
Here's a star. This is what happens to it. So for a theorist, this is what we need to do: somehow take this star and make it be bright. And at the time that it explodes, it's usually brighter than its whole host galaxy, more powerful than its whole host galaxy for a brief amount of time. So it makes these bright objects. They're easy to find. So we now discover lots of these every year. We actually have a growing set of the progenitors observed prior to the explosion, so we're learning more and more about these. And what did we learn from this 1987A, which was the classic one? It was so close that we saw neutrinos coming from the core collapse. So it taught us a couple things. One was that we saw the progenitors, so we now know that supernova can occur from massive stars. So they occur in something that was previously a massive star that then is destroyed in it. The problem with it is that the massive star of 87A did not look at all like what the theorists thought it would. So the theorists, although they said it should be a massive star, they were wrong on what the star should look like. It turns out that almost every nearby supernova looks weird to the theorists. I don't know if that should be something wrong with the theorists, or maybe it's the observers need to get better supernova. But it did look very weird. We think we understand it now. We think binary effects were involved. But it is still and you guys can correct me, it is still kind of a weird light curve. It was not a normal supernova light curve compared to a lot of the type 2, the core collapse supernova. We knew that it had to produce in a core collapse, because the only way you're going to get these neutrinos that we saw is if you have something collapse to something quite compact. So you're going to have to take that star and take the core and collapse it down to nuclear densities to make this explosion. So we learned those two facts. But with that, that really doesn't tell you much about the engine, other than it has to be something around a neutron star, which we've thought since the 30s. So we actually thought this from the 30s, that it would be a collapse of a core down to a neutron star, but we didn't really know how do we get that energy. And there's a lot of different engines that are still being discussed today. There's this convective engine that I'm going to go into detail. The things that I'm not going to go into detail are things that people have been bringing up. Magnetar, which is you collapse down to a neutron star, you make very strong magnetic fields. So something like 10 to the 15 Gauss, 10 to the 16 Gauss. You have a rotating neutron star with a strong magnetic field, and it can drive emissions. So this is one of the engines that people have been proposing. And I will refer back to this engine as we go through. We think that this might explain some bizarre supernova. The other one is you can make an accretion disk around that compact object. And the classic example of this is the current standard model for long duration gamma ray bursts, which is the idea is that it's a black hole with an accretion disk, and that accretion disk drives a jet, and that jet is the gamma ray burst. So there's accretion disk mechanisms as well. So what I want to understand is, okay, so I have these different engines. Why do we think this engine works for normal supernova? So I think these engines are going to explain weird things like hypernova, long duration gamma ray bursts, perhaps even these ultraluminous supernova. But for most supernova, what is the engine behind it? And to get at that, let's start with the progenitor. I don't know how many people have seen these diagrams. They're called Kippenhahn diagrams. They are as much information as you can get in a glance at a star's evolution. On this axis is the mass of the star enclosed. So this is the core. As I move out, this is the envelope. So this is 0, 5, 10, 15, 20 solar masses. This is a 22 solar mass star initially. On this is time until collapse. And it's in log. So this is 10 to the 6 years, 10 to the 4 years, 100 years, 1 year, and you're going down here, a 100th of a year, so a little, a few days, down to seconds before collapse. So I'm looking at the structure of the star as a function of time as I move out this way. So if you look at the top here, you have a massive star that's blowing a wind. So this first phase is the hydrogen burning phase. So this is when I'm burning hydrogen in the core, and the star evolves. And then at the end of that first 10 million years or so, it's burned all the hydrogen in the core and built up this helium center. And it isn't burning, it expands, and that core compresses, and that core starts to burn the helium, so you go through a helium burning phase. The star expands, and it blows a pretty strong wind in, so it loses a lot of mass then. So it was maybe a little over 21 solar masses at the end of hydrogen burning. Through helium burning, it's lost, another 6 solar masses. And so this particular star ends its life as a little less than 15 solar mass star. When I talk about stars, I always talk about their initial mass, their 0-age main sequence mass. So if I say I have a 25 solar mass star, I'm assuming that that's the star's mass at the beginning of its life. Unless the star is really massive, this mass loss doesn't change the core much. And for a core collapse engine, we only care about this inner portion. So here, if you look on this stage and you're looking at the core, you see hydrogen burning, you see helium burning. Then you get a phase where you have helium burning only in the shell on top of that core. And that's what's supporting the star. In fact, this is a plot by Alex Hager, and he does this thing where he colors it where neutrinos are losing energy. So in this purple range, that's parts of the star. So at 10 to the 4 years, the inner core of the star is just cooling via neutrinos. So he's cooling via neutrinos, and then the blue is where he's generating heat through things like helium shell burning. And these dashed lines are where it's convective. So it tells you everything, it really does. So you can actually, if you want to go see people talk about the onion skin of a star, I went to helium burning, so I now built a carbon core here. So wherever the burning ends, the ash is the new core, so this is the carbon core. And then I get carbon burning. And so I burn first carbon in the very center of the core, burns in the shell, burns on the outside of the shell, and now I have a oxygen core. And then I start oxygen burning. So this is oxygen burning. So now in here I have a silicon core. And then the silicon starts burning. So now I'm making up an iron core. And so this series of silicon burning makes an iron core in the center. For a core collapse engine person, we care about the inner 3 solar masses. I only care about this part. Whether I succeed or fail will depend mostly on this inner 3 solar masses, maybe the inner 4. But this is the region where I care. So it's where all this activity is going on. So this would be a nice star. This would not have looked at all like 1987A. And it would not be something that matches some of the observations. What we have realized with stars is that when you have these convective burning phases, we model these in 1D. We model these in 1D and we assume that we can do a prescription for the mixing and it'll get the right answer. And the problem is with that prescription is it does a nice smooth mixing, and if it doesn't do a smooth mixing, it has some of the material go too far in than it should, it actually blows up and usually crashes the code. What the typical stellar anemometer does is he stops the code, then goes back, changes the time step, and let it go some more, and it eventually evolves. But it's one of these why it's hard to model these stars. The question is what happens in nature, and when we started doing multi-D calculations, we realized that this nice smooth mixing layer does not happen the way we thought. And Dave Arnett has been saying this for ages, so there's Smith and Arnett et al., or there's some recent papers. But Falk Herwig and Paul Woodward have also done some calculations of this. And this is a burning layer. In this case, it's a helium burning layer, but this is a burning layer where you have the core of the star, and this is that burning shell. We talked about shell burning. This is that shell burning, and this is colored by vorticity, but it's showing you that mixing, and the mixing actually starts to slosh back and forth. It's something very different than a smooth kind of recipe kind of burning phase. And in fact, this particular calculation starts sloshing back and forth until it gets explosive, bursts, sends some material out. Most of it will, just puffs up the star a little bit and then comes back down, but it's causing oscillations in the star. And in fact, now we think some of the oscillations we see in stars are caused by this very excited burning, this very, very different than normal mixing link theory would predict, this kind of explosive convective burning. And Dave Arnett has probably said it best where he was modeling some silicon burning. So this is, again, at the very end stages of the life of the star. It's right here at the silicon burning starts at the 3 days before death kind of thing. So it's 3 days before the end of the life of the star. And his silicon burning is a series of just explosions. It's not burning in this nice mixing link picture. It's actually igniting, exploding, coming back down, burning, exploding, coming back down for only 3 days of its life. But these stars do not, even up until, they're going to explode in the end, but even coming up to it, they're getting quite explosive as they evolve. So this shell burning has been different than we thought. Why do we believe this theory? What do we trust? Why would we trust this kind of model? Yeah.
Is this a 3D?
Yeah, this is a slice of the
4 pi
3D.
calculation.
Yeah, and you can't do it if you don't do the full 4 pi. So this is what the hydrodynamics is telling us. One of the features of this is we took Dave Arnett made a new recipe for nuclear burning based for his 1D code, because we still have to model these stars in 1D, and we started to look at what does that change in our models. And this is a story of why you should never work with me. I was giving a student of mine some stars to explode and make supernova of, and I wanted to look at a 1B supernova. So I told her to remove the hydrogen envelope, and then we would use that, we'd take that and get down to the helium layer. So I said, go down to the helium layer, and then we'll explode the star at the helium layer. So remove everything above the helium layer. And so I sent her this particular star, and this is enclosed mass going out, 0, 2, 4, 6, 8. I'm just showing this. This is a 15 solar mass star, so this is just the inner portion. The dashed black line here is the hydrogen envelope. This is helium right here, and this should already be sending you signals if you've ever looked at a star structure. You expect it a hydrogen layer, and then below it a helium layer. But if you look at this, so I handed it to her and she said, where's the helium layer? And I said, can't you just look at the abundances and see where it's mostly helium? It turns out this is the helium layer. This whole region should have been the helium layer. But what's happened with this extended mixing is a lot of that helium got burned into oxygen by doing some mixing that was more extended than you would expect with a standard mixing ring theory for your convection. So normally this star would look something like, this would be the end of the oxygen layer, this cyan colored line, and then you'd have the helium come up and go down like this. Instead, all of this got burned and it was turned to just 30% helium and 60% oxygen plus other elements. If I looked at a more massive star, here's a 27 solar mass star, that helium layer, which should be right here, has gone down to about 15% helium. So we remove a lot of the helium. The interesting feature is, as I go to more massive stars, this is a bigger effect. And the interesting observation that makes me start believing that maybe this is a real effect is that when we look at these hypernova, these supernova produced in gamma ray burst observations, supernova that we think are occurring in the most massive progenitors, we don't see any helium in a lot of those. We don't see helium lines. And one way to get get rid of that helium line is to burn it before you collapse. So there's ways to burn it, and this may be another way to get rid of that helium. So it turns out that this mixing may be an answer to some of the puzzles that we've been dealing with these gamma ray burst observations. So we have these models. We now know there's lots of uncertainties in them. But if I get them, I can take a core, and we've been doing this so I've been doing it since my grad school career. But we have been collapsing stars since the 60s. We've been taking stars. We've been they go unstable what happens is you build up this iron core. You're adding more iron on top because you're burning silicon on top. You need that silicon burning to keep the star alive, and it's adding more and more iron. Suddenly, the iron core is so massive it starts to compress. And it's being supported by two things, thermal pressure and electron degeneracy pressure. But as it compresses, I can get electron capture onto the protons, again, neutron and neutrino, and that removes the electron degeneracy pressure, so it's going to collapse even further. I also do things where I take the iron and I disassociate it into alpha particles, and that removes some of the thermal energy. So I start to I compress a little bit, I remove some of that pressure, then it wants to compress some more. That accelerates the electron capture, it accelerates the dissociation of the iron atoms, and suddenly I have this runaway collapse. And this is a simulation of that runaway. It's a 3D simulation, just showing you in 1D, where this is radius 1, 10, 100, 1,000 kilometers, and this is going at minus a tenth the speed of light, and this is 0, so it's all falling in, and you see this collapse that's going in at nearly a tenth the speed of light. And in fact, this little blip here is all caused just by the fact that there's some nuclear burning going on, and it's adding a little bit of energy, but it's not enough to make it escape the collapse. So it falls in, it has this little blip, but it ends up collapsing, and it keeps on falling in until it reaches nuclear density. So 10 to the 14, roughly 10 to the 14 grams per centimeter cubed. So at 10 to the 14 grams per centimeter cubed, you suddenly get neutron degeneracy pressure, nuclear forces, and it halts the collapse, and it bounces. And this was actually the original proposed model for how you were going to make a supernova. You're going to collapse down, you're going to release all that potential energy, and it's going to drive a bounce shock up, and it'll make an explosion. So this in the 60s, Colgate and there's two Colgate papers, but I'll just cite the Colgate and White paper, had done calculations where the Colgate and White one, they had neutrinos, so it must have been Colgate and Johnson. They did a paper where they just looked at the bounce and said, this is the explosion. It comes in, it bounces, and drives out a shock. And so here's that shock going out. This is 1, 10, 100 kilometers. This is minus 0.15 times the speed of light. This is 0.1 times the speed of light. So it's going nearly 8 or 9% the speed of light, moving out this bounce shock. And it's just flinging outward. In these densities, photons are, of course, completely trapped. Even at 10 to 11 grams per centimeter cubed, your photons aren't moving at all. Neutrinos are trapped. And they stay trapped until the shock moves out enough, about 100 kilometers, 200 kilometers, when suddenly the densities get low enough that the neutrinos can stream out. And that's what Colgate and Johnson didn't have in their code, is the neutrino losses. When people included that, all the neutrinos leaked out and the shock stalled. Because that's all the energy was held in that thermal energy, was all neutrinos. And when the neutrinos could leak out, the thermal energy went away and the shock stalls, and it made this stalled shock front. So the picture that we've had for many years, at least since the early 90s, is the following, not even, probably the late 80s, is you have that star, it's collapsed down. Here's that protoneutron star. The core is collapsed down into this about 20, 30 kilometer core. It's going to cool and eventually become a 10 kilometer neutron star. It's collapsed down here. It's emitting neutrinos. It's radiating neutrinos. It sent a shock out, and that shock stalled at a couple hundred kilometers. So here's that stalled shock here. I have the rest of the star falling in. So the rest of the star has just realized that its core is imploded on it, and it's falling in onto the core. So it's piling up at the place where the shock stalled, and you have this region that's convectively unstable. And what we have been working on for the convective region is finding out how is this convectively unstable. And this is where we argue. If you go to a meeting where you go where all the aficionados are, they will argue about what is the nature of the convection. Some will say, oh, it's a vortical acoustic instability. Some will say it's Rayleigh-Taylor. But they're still arguing about just what instability is here. There is an instability there. This is what we're studying, is this instability. I was pushing the Rayleigh-Taylor, so that's why it says entropy-driven convection. It does not need to be. It could be different instabilities. The reason I still am pro-Rayleigh-Taylor instability is entropy-driven convection. Entropy-driven is just I have hot material below cold material. It's going to want to rise. The advantage of that particular instability is it grows quickly. So it will be a quick instability. So you have that instability, and you somehow have to take this energy, either energy from the matter accreting or energy from the protoneutron star, and revive the shock and drive an explosion. So the alternate engines are, you could have magnetic fields play a role here. If this is where, if I had a rotating neutron star and it had strong magnetic fields, it could drive a magnetar. So these are all the models that you're thinking about. How do I take this core and make it drive an explosion? So this is the picture we have. And this is a slice of it in 3D. So here's that protoneutron star. Here's the infalling star. The arrows denote the velocity of the material. The colors are the entropy. So this is high entropy material. This is low entropy material. So material comes on top of the protoneutron star. It convects downward and flows. And it goes onto the protoneutron star, and bubbles rise. And when this can drive an explosion is when you actually get a supernova. If you don't, if you can't push this shell off, you form a black hole. And that's one of the things that we have to have with any engine, is it has to be able to produce both neutron stars and black holes. So it can't be something that's uniformly always successful, because then you wouldn't get black holes. So what kind of features can we explain with this? One is we can look at the accretion rate of these stars. So different stars have different infall rates. Their density structure is different. So what's falling on top of this envelope, what's falling down here, is different for different stars. And you can imagine if it's light, if it's only a little bit of material, it's easier to explode. In fact, we think of it as a lid on top of that convective region. It's like you have a pressure cooker. And if that lid is only loosely held, because the infall rate is not that high, it's easy to explode. So you might imagine, here's 3 different stars from Stan Luzzi, a 15, a 25, and a 40 solar mass star. The 15 solar mass star, that infall rate drops quite rapidly early on. So you might imagine it's easier to explode than a very massive star like a 40 solar mass star that has a higher accretion rate. So we worked, we've studied this. This is something that Burroughs and Goshi discussed at some point, where we kind of had this idea that it's going to be hard to explode more massive stars. So the trend that we made with, we realized with our calculations is more massive stars are harder to explode. Here's some old calculations where we looked at a 15 and a 25 solar mass star. These are time evolution, where the 15 solar mass star, remember its infall rate drops really rapidly. It explodes quite quickly within, this is 50 milliseconds, 50 milliseconds, 90 milliseconds, 140 milliseconds, 250 milliseconds. So at 90 milliseconds, it's already starting to explode. for a 25 solar mass star, it struggles to explode. This is 50 again, 90, 140, and this is 250. It doesn't explode till 250 milliseconds after the collapse. This is actually not so unaligned with, this is at roughly 90 milliseconds here, this is at 250 milliseconds, this drop in the 25 solar mass star inflow rate. So this is probably just indicative of the star structure, but when these exploded, this produced a much weaker explosion than this 15 solar mass star. And in fact, this is what we argued would be the distribution of explosion energies. These were simulations, this was our fit to them. What we argued was that at between about 8 to 20 or so solar masses, we get explosions that were above 10 to the 51 ergs, and above that we get weak explosions that that would be on the order of a half of 10 to the 51 ergs. The interesting feature there is the binding energy of the star goes up dramatically at around 20 solar masses. So when these two lines crossed was when you would expect that you are not forming neutron stars anymore, you're forming black holes. So we called this the line between neutron star formation and black hole formation. But this is also the line roughly where you get strong supernova explosions and weak supernova explosions that may be difficult to see because they don't eject much radioactive material to power them. So we have a bright supernova weak. Yes, sir.
Sorry, what happened to blue line? Sorry, again,
This one and this one? This is me just saying, what happens if I was off by a factor of 10 in the energy?
Oh.
This line is still in the same place because of this binding energy. So it turns out that even though I say 20 or so, but it's you could do 21 plus or minus 3, and even if I was off by an order of magnitude, it would still be the same.
For 87A, it was in the 20 solar mass range.
Yeah, the latest presenters I've seen has pushed it down some. So, but this is I put it at 18, I think. So this is what we kind of envisioned. We also envisioned some that don't explode at all, and where this line is harder to determine, and it depends on our simulations. And I will say that Tony Mazzacappa has recently published a paper where the energy kind of goes, the energy is more like this, so it's a little broader. The cutoff is still going to be roughly at the same point, but he's for where do you form a fallback black hole versus a neutron star, but he has a different curve. So that's one of the things that our model then predicts and explains is that we both are arguing that we have a way of getting both strong supernova and then black hole forming systems. We also say that boy, there shouldn't be that many stars that are above 20 solar masses forming supernova. Now there is a caveat to that. If you have a lot of mass loss, a 50 solar mass star ends its life. In fact, Stan Woolley has some progenitors where a 50 solar mass star ends its life as a 3 solar mass star. That's going to form a supernova, so don't count those. But if you don't have much mass loss, there is a cutoff that you should expect above 20 solar masses not to have that many supernova. The other thing that we can explain is this convective engine that we have, where we're depositing energy here. When that energy is enough to drive off the material that's piling up on it, when it has enough energy to push that away, it will explode, and the energy, I won't deposit that much more energy. I can maybe deposit a factor of 2 more, just continuing the engine a little bit more longer. But once the shock starts moving away, the energy source, whether it be neutrinos, the neutrinos are no longer getting absorbed, so I'm not adding much more energy, so I can predict how much energy is the maximum energy I can produce in such an explosion. So, and it's not just the maximum, how much energy is what I expect from such an explosion. And if it explodes quickly, so I can do that as a function of time, as I just look at the infall rate, what's the pressure on top, how much energy do I need to blow off this lid that I have. If it's a rapid explosion, it predicts that I should get, most of my explosions should be around 1 to 3 times 10 to the 51 ergs. So the interesting feature with this mechanism is even though we've released 10 to the 53 ergs of potential energy in the collapse, the explosion is always going to be 1 to 3 times 10 to the 51 ergs. So already I can't explain some of these bizarre supernovae. I can't explain a hypernova with this. So this cannot be the hypernova. But it has a natural explanation of why normal supernovae tend to be only a few % efficient in how much energy that they produce. Now, if the explosion is delayed, it will produce much weaker explosions, and this is what we're seeing in our engine calculations. If we don't explode quickly, we get weak explosions. Now, if you instead had you could do the same thing with, say, a magnetar engine. You could say, I have a magnetar, it's producing energy, and depending on the rotation, I get a explosion energy. The hard thing for me to understand is, why does that magnetar, because then I can explain all the way from hypernova all the way down to normal supernova. Why are most stars spinning at a rate that they produce only 10 to the 51, 10 to the 50, a few times 10 to the 51 ergs? So that would be the explanation. The problem with magnetar, people who invoke magnetar can explain everything with it. What they have to then explain is, why do they get the exact observations we see, where we see a lot of supernova in this range? And if this is not the observation, then I'm in trouble.
I'm just struck by the inefficiency of it. This is just my ignorance. So this is the 10 to 51 ergs is the photon luminosity, so the radiation.
It's the total supernova, is the kinetic energy of the supernova.
It doesn't include, for example, the neutrinos.
It does not include the neutrinos. So
Sure.
most of the energy comes out in neutrinos.
Got it.
Yeah, because when you take the 87A neutrinos, that implies 10 to the 53.
Yeah.
Okay.
So there's a 10 to
Okay.
53 ergs emitted, but it all comes out in neutrinos and not in explosion energy. So if instead I had a magnetar, I could get 10 to the 52 ergs, right? I could get whatever, and in fact, that's what we're invoking for long duration gamma ray bursts. We're invoking, we're going to get more efficient than that. We're going to take that, or we're going to, well, in most cases, we're more efficient. We're going to take an accretion disk and somehow get 10 to the 52 ergs. So, how does this stand up to observation? So one of the things I said was there was a, there was a trend in masses for these objects. We expect that more massive stars don't explode. Mario Hamway did a thesis where he took some simple light curve models, and he used fits to that and said, what are the ejecta masses that he predicts for the supernova he's observing? And he got ejecta masses that were all at the level of 40 solar masses. There was a 27, I think the lowest was this 17 solar mass. But the ejecta masses ranged from 17 up to 56 solar masses. Now, the problem with this is, so imagine this had a core of 1.4, so it's almost 20 solar masses above. I just told you that theory argued that we don't explode, we don't make supernova with these progenitors, because clearly this is not going to be 56 solar masses of ejecta. I can't fit that into a star that's 20 solar masses or less. So I have a problem. And I will tell you what we theorists decided. We decided this had to be wrong. And I think most people did. And what it was, and we'll go into this in some more detail, was that these simple light curve models can lead you astray. So this is what the supernova light curves had told us from Mario Hamway's thesis. This is what we have now where we've looked at progenitors. And this was probably also fraught with errors and concerns. But these are the set of systems that, using the HST archive, have looked at the progenitor. So they look at the HST, it has lots of observations. The supernova goes off. They go look, do we have an image of that field in HST prior to the explosion? Let the explosion go away and look, are any stars gone that used to be there? Can we see where the star was that formed this? And they can place, unfortunately, most of the stars, they just have upper limits. But they started to increase the set of progenitor, what we know about the progenitor for systems where we've actually observed them. So 87A was one that we got lucky when we saw a progenitor. It turns out that for these, they all lie roughly below 20 solar masses. And in fact, they are what you might expect from a normal IMF going from 8 to 20 distribution of stars. So and in fact, if 30 solar mass stars were exploding more commonly, we would see at least a couple in this sample, and we haven't. So it looks like the data is going back the way of theory, what the theory prediction is. So the convective engine said it can't be that many explosions above 20 solar masses. It looks like the data is starting to support that.
I see. Sorry, maybe you said this already, but for the direct collapse of a very massive star into a black hole, is there any observational significance?
So if it's rotating, it'll So it collapses down to a black hole. If it's not rotating, it just collapses down to a black hole. Maybe you get some X-ray emission at the very end of it, but it's not that bright. But if it's, and so in fact, Ohio, University of Ohio, or the one
Ohio State.
Ohio State, they're looking at
Yeah.
lots of massive stars to look for them to just
The
disappear.
failed ones.
Yeah, so they're looking for those fails. But if it's rotating, you can form an accretion disk around it, and that's what we think is how long duration gamma ray bursts are produced. What this also told me is that we need to do some more work on how we do supernova light curves. Because clearly, the Mara's thesis, his observations weren't bad. I think his theory was too simplistic. And I just want to briefly go into some of the problems here. The problem with modeling supernova is that there's an amazing, the light curves of it, is it's actually a rich physics field. It's a rich physics field that has been studied a lot at the national labs. It is not there's a lot of problems in trying to model it. We talked a little bit about the initial conditions, but just in the radiation transport, you need to solve, we're trying to solve the Boltzmann equation, but we don't want to spend all that much computational time, so we make approximations. And those of you that were around when you had the Peter Hufflick versus Phil Pinto arguments, they were essentially just arguing about what approximations they made in solving the Boltzmann equation. The opacities have a lot of issues with them. How do we calculate the opacities? Are they in local thermodynamic equilibrium or not? If they're not, it's harder. Can we make approximations? How wrong will those opacities being wrong, how will they affect our results? The ion-electron coupling, which I thought we all just assumed that ions and electrons, at least in the light curve, were well coupled. At least when we see these X-ray bright bursts, we know that probably they're not coupled that much. And that's an assumption we make in most of our light curves. In radiation hydrodynamics, that's if I'm just doing transport by itself. But really that radiation couples to the hydrodynamics, and you have to model them together. And that makes the problem much, much more difficult. And we start to make more approximations in how we do the coupling. A lot of people still model that when they do a supernova, they model it hydrodynamically out, and then they do a post-process transport on top. And that will not give you the right answer. So there's a lot of errors that can change the results. It may seem daunting. It's worth doing it right. If we really want to use this data to constrain the engine, we have to do it right. This is just, here's the Boltzmann equation. Some of the approximations that are made is you average over the angle. If you take just the first moment, you can just do diffusion, or flux limit diffusion. If you take higher moments, you can do variable Eddington factors. You can average over the energy groups to make it simpler. Otherwise it gets, Phil Pinto always likes to brag about having a 7-dimensional problem. The energy groups, you can do gray, and then you only have one group for your energy, but you're going to get the wrong answer then. You can remove the time-dependent term and just assume that it's a steady state. That is a lot of what Peter Hufflick did in his approximation. But he did better angular studies than Phil Pinto. And then you can also ignore spatial terms. Some of the neutrino transport that's done today, people are doing a series of 1D neutrino calculations, even in their multi-D hydro calculations. So there's lots of approximations you can do. If you go to opacities, especially if you're looking at things like, there's a transient called a kilonova. It's two neutron stars merging, and they eject some of this neutron-rich material comes out in the form of heavy elements like lanthanides. If you really want to model that, the opacities can get really complex, and you're talking about 300 billion lines. So that you would have to include, and I just want to briefly go over this. This is what it looks like trying to model. This is samarium Z62 element. It's all these lines, and if you try to do it, turns out that in this calculation we threw out most of those 300 million lines. So this is only 0.1% of the lines, and that would be great. Except that here's with those lines thrown out. Here's if we include those lines, but broaden them a little bit so that we can account for them in our calculation. This is how it changed the opacity. So we had thrown out a whole bunch of lines here, and when we included them, it changed the average opacity in these wavelengths by a huge amount. And that should only bother you if you're, so I'm not an observer, so I don't care, but apparently this is easy to observe in this area.
Yeah.
If you push down into here, it gets harder to observe. And they, you know, so it's not so easy to observe these kilonova. And the reason they're exciting, they're hot because LIGO is going to detect neutron stars merging and in gravitational waves. So we'll see the gravitational waves, and the question is, will we see any optical outbursts from these gravitational waves events? And if they're pointed out as we think they'll form a gamma ray burst, and we'll see it. But if they're not pointed out as this kilonova was going to be our saving grace. But unfortunately, when we calculate this better, the infrareds, you know, can be bright for a reasonable amount of time. This is log time in days, so this is 1 day, 10 days. The infrared stays right for 10 days. But the optical and the near IR are bright, but only for less than a day. It's going to be really hard to observe these in the optical and the near IR. And this changed only because we calculated the opacities better. So this is the kind of, and in fact, if you looked at the old results, they had, when they weren't doing the opacities correct, the optical was bright at 10 days, and it was, you know, over in this range. So it's, you know, more than an order of magnitude difference in the optical light curve.
What are you calling near
What did I?
0.1 keV. Oh, sorry, 0.1 eV.
Yeah, I think that's right. I looked it up on Wikipedia, so you did asking Ferris what are these, but I think it's 0.1 eV.
Just about a.
And then just as one other comment, this is the other thing that I've been harping on is, if I don't couple the radiation to the hydrodynamics, I do a nice hydroshock, I could use the set-off solution even, and then just do a post-process. The problem is, here's a shock moving out, here's the velocity. So here's that shock moving out, this is the reverse shock. Shock moving out, reverse shock moving in, shock moving out. And what's this? This is actually, the radiation starts to leave the shock and accelerate the material ahead of it. So the radiation has finally gotten untrapped and is accelerating the material ahead of it. And if I wait a little bit longer, here it is accelerating. In fact, it's such a nasty calculation that it's going a little bit unstable in my calculation. But here it is. It's made this kind of, it's defining the shock velocity. It's changing what it would be if I just did. If I did a normal set-off thing, this would just keep on going out. So this is what happens if you start doing the full calculation. Even the explosions will be different. And so all these little analytic tricks we're doing to calculate light curves, they're fine, they're just off. They don't have this effect at all. So if you really want to do detailed science, we're going to have to calculate this completely. And unfortunately, I thought this was going to be an easy problem. So in defense of my 3 years, thinking I could get this done in 3 years, I thought, okay, they've done most of the steps. When I do this, it'll just be refining things. It'll be all good. No, it's an order of magnitude difference in things. So we're making order of magnitude differences still in how we model these light curves. So there's a lot more theory to be done. Fortunately, there's good people working on them, but there's room for more people. Whoever wants to work on it, let me know. I'd be happy to work with anybody on this. So that's...
When you say radiation, that includes the neutrinos, right?
Yes, but the neutrinos are down at the core, and they're pretty much leaking out. And when we're modeling these light curves, they're trivial to do. So the neutrinos we worry about only in the very center of the core. So I just want to briefly go over the last two kinds of constraints we have on that. One is the ejector remnant, so you can explode the star and let it move out, and then look at the remnant at late times. And we have some beautiful examples of these: the Cassiopeia supernova remnant, the Tycho supernova remnant. You see these, they're pretty pictures. They look like they have nice turbulence going in them. They're great. They're great laboratories for studying turbulence. And there's a whole, Chandra has looked at these a lot. We have a lot of information on them. With this convective engine, this is a 3D, it's a slide just of the outflows going outward. This is what the outflows look like. So you see that it's not a bipolar ejection, but it is a low mode ejection of material. So that's what we expect out of these supernova, the convective supernova engine. It's not a jet-like thing, but like kind of these outflows going outward. And this is, I think, the clincher for me of what the explosion is. This is a plot of the Cassiopeia remnant. This, let's see, this is iron, the green is iron, the red is silicon, and the cyan color is titanium-44. And when you look at a supernova remnant, you have to worry about how did you get the observations. first of all, the iron and the silicon, you're only seeing if it's shocked. So the shock is moving out. The stuff that gets heated, that's what you're seeing. So you're seeing the stuff that's been shocked, and it sends a reverse shock back, so it sends a shock inward, and that's the part that's bright. So you're not seeing all the iron, and you're not seeing all the silicon. In fact, a lot of the silicon and iron you're seeing is not from the supernova, it's from the surrounding medium. So you're just seeing that material. And so people for the longest time said, oh, it has a jet, because the silicon looked like this. And Roger Chevalier and Blondin, I guess Blondin and Chevalier had a paper where they said, no, this is just asymmetric surroundings. This is not a jet. Supernova remnant people, most of them would tell you, no, no, it's a jet. In fact, on a Chandra observation, the big, where we observed it for 30 days, looked at this remnant, the Martin Landing wanted to say, here's our jet. And we said, we don't know that. We don't know it's a jet. The titanium-44 is different. We're observing it with the new star satellite, and we're looking at the decay lines from radioactive titanium-44. We are seeing all the titanium-44. So where's the titanium-44? Well, there's a bunch going in this direction, there's a bunch going in this direction, there's a bunch going here, there's a bunch here. But it's actually in this globby material, it's not a jet. This is what is telling you what the explosion engine is. The titanium-44 is made in the same place the iron is. In fact, you can make titanium without making iron, but it's hard, and you can make only a little bit of titanium where you make iron. But mostly the titanium is directly situated with the iron that's synthesized in the supernova. So where the iron is actually produced in the supernova, that's where the titanium is. So this tells you what the asymmetry in the explosion is. There is not a jet of titanium going out this direction. This was probably not a jet. This was probably this kind of bubbling kind of explosion. I don't see any way to get an explosion mechanism that is jet-like to work for this explosion. So at this point, this is what you have to convince me you have a model for if you want me to turn away from the convective engine. I think this is pretty much sealing.
But you don't have rotation in it. You don't have magnetic field in it.
Yeah, but if I did and it made a jet, if magnetic fields were important, they would probably have a single bipolar feature, and it's not in this. So I would argue Cassé, bipolar, the magnetic field did not play a big role.
Rotation as well.
Yeah, rotation played a minor role. And that's what it does in most, if I get the best stellar model from somebody and they give me the rotation of it, the rotation cannot play a big role in the explosion. Now, that's not to say that for special stars you can get it, but for a normal supernova, I think you can't do this. So that's, I think, one of the last pieces of big data. And then the only other thing that the game we're playing now is, remember I was showing you guys this where I have the explosions. I can look at the remnant masses. I can look at I can do more detail. What is the binding energy of the envelope? And ask the question, I have these explosion energies, what kind of distribution of masses do I get? So as a function of initial stellar mass, I can predict the remnant mass for a set of progenitors. And there's a weird feature in the progenitors where this is the remnant mass at the end. So this is that 20 solar mass, they're making neutron stars. Then I make black holes, and then I make lower mass black holes, and then I make big black holes again. I get a slightly stronger explosion at around 25 solar masses. This is just a feature of the progenitors that we have right now. This is from Alex Hager and Stan Mosley. But we can start making predictions about progenitor masses, and we can compare them to observations. And one of the big observations that's been puzzling us is that it looks like if I look at mass versus number of systems, there's a whole bunch of neutron star masses going up to 2 solar masses. Then there's a gap, and then black holes don't start until you get around 4.5, 5 solar masses and beyond. So there's a gap between neutron stars and black holes. And what this tells me is there can't be that many supernovae that have a lot of fallback that fill in that range between neutron star and black hole. And so we worked really hard and we found a way to say, the explosion mechanism can't be, this picture actually tells me that this picture is wrong. It can't be so gradual as this. It's going to have to drop off like this, much harsher, to try and make it. So this part of my simulations must be wrong. if this gap is truly there. But we did produce models where we do get this, can get this gap, and then we can compare it to things like neutron star mass distributions. We have predictions for the neutron star and black hole mass distributions. The problem is we don't have that many double neutron star systems. This is the mass of double neutron star systems. This is the number. This is the prediction from population synthesis. So it says there should be a peak at this 1.2 to 1.4 solar mass range. But this is a log plot. So, if you see 10 systems, they're all going to be around in this range. And this is what we see. They're all in this range. But that's because we only have less than 10 systems with really accurate masses. Hopefully in the LIGO, advanced LIGO era, the number will get broader, and we'll see if we find more systems that broaden out and actually match this distribution. So this is another game we can play. So looking at all these observations, we can start to place some constraints on these systems. And I'm going to end there. My only other thing is that it looks like black holes are getting kicks as well, and that may be telling us something's wrong with the explosion mechanism. So let me just go through the summary. I think the evidence is growing that this convective picture is at the heart of most normal supernova. It's a natural explanation for the inefficiency of the supernova explosion. 10 to the 53 ergs is released. 99% of it comes out in neutrinos and does not, we don't convert that neutrino energy into some kind of kinetic explosion. The trends with progenitor mass, it looks like we outlasted the observers and argue that most of these normal supernovae should happen between 8 and 20 solar masses, and it looks like progenitors are now saying that. The ejective distribution matches this kind of low mode convection that we're seeing in our models. The remnant masses can place some constraints on exactly the nature of this explosion engine if we can use those as well, but we need a lot more data to do that. And I think we can learn a lot from supernova light curves, but there's a lot of work to do to really get detailed quantitative knowledge from that. If we really want to use supernova light curves to constrain the engine, supernova light curves are great at constraining what is the radius of the star, what is the, you can use them to do that kind of observations. What's the circumstellar medium? We do that a lot with the light curves, but if I want to get down to the engine, we're going to have to do the detailed physics correctly, and there's a lot of work to be done there. And we actually are working on ways to improve what we do there, things like the opacities. Los Alamos has a opacity project that we're working on with Sandia National Lab, and now hopefully Ryan here at TAMU, we're actually trying to get a team to study these opacities better and see if we can improve what we know about the supernova opacities. And I didn't talk about it, but if we want to discuss it, the black hole kicks have some good surprises that you can actually, there's some nice stuff we can do, I think, with weird observations like this. So it turns out that there's a lot of interesting data that you can pull together to start learning about the supernova engine. And if we start pulling it together, I think we are starting to constrain what the mechanisms are. And I'll end there.
I'm surprised that, since the bounds come from collapsing back to nuclear density, you make no mention of nuclear equation of state. Are you totally sensitive to that?
No, it's, in fact, that's an important piece of physics. I just didn't, that's a whole talk in itself. So there's in fact, there was a push by Hans Bethe and Jerry Brown where they wanted it, depending on how hard or how stiff that equation of state is, it can change the bounce and how far it goes, and that can make a big difference in the explosion. With the current equations, although that's important, with the current equations of state, if you just did a one-dimensional calculation, you still would not get the explosion no matter what you did. We really do need that convective portion to be there as well. But getting the right equation of state does change what are the conditions right after bounce that then that convective engine moves in, and it can make the difference between an easy or hard explosion. There are not that many hot equations of state. There's a lot of neutron star equations of state for cold neutron star matter. If you want to also add thermal component, there's some difficulties, and generally those that are created we have used and looked at what their effect is. And it is it and things like neutrino cross sections are 10 to 30% effects on this, which can change, in the broad scheme, it's just gonna change that line of where do you get explosion and where do you not. But things like detailed nucleosynthetic yields, we're not gonna do until we get that kind of physics right as well. And that's, we have whole meetings on how to improve that in our codes. So it is an important thing, but I skipped it for this stuff.
Yeah, actually, I want to talk a little bit more about your last bullet point. So pulsar kicks and black hole kicks, are these actually of any use? There's the debate that I see it typically framed as exotic new physics versus some sort of asymmetries in the collapse that causes these kicks. What's your thoughts?
And that is the debate. And the issue is that if the kicks were just for neutron stars, we have a couple models for this. The picture that I had in my mind for the longest time was, so neutron stars, you're going to get a nice explosion. It's going to have asymmetric ejecta. It's going to do slow mode convection. It's going to drive off bubbles. The kick is going to be in the opposite. The compact remnant is going to go in the opposite direction of the ejecta. That's great. We struggle to get the highest velocity kicks, but it still all seems to hold together. So I'm happy with that. Then we started seeing black holes with kicks. I can still do that if I assume those black holes were formed. I had the ejecta, and then some material fell back down, and I still get a kick. And so in fact, we had what we use in our population synthesis models is we assume that those kicks had the same momentum of ejecta, but the velocity of the black hole was lower because it has more mass. So that velocity of the kick would be the velocity of the neutron star systems divided by the mass, the ratio of the neutron star mass to the black hole mass. So it would be a smaller kick. The problem we're having is that it looks like black holes have big kicks on par with the neutron star kicks.
So how many black holes have kicks? So there's a handful from your figure in that distribution.
Yeah, and there's
only a handful of black holes, period.
There's only a handful of black holes. There has been a population study, and Serena Repetto, published 2 years ago, where she said she needed the kicks to be on par with the neutron. So she just looked at the black hole system, so it's like 10. But she said all of those needed to have kicks that were on par with what neutron stars get. Now, that may be wrong, and I'm hoping it's wrong, because if that's true, the only way to do kicks is by some neutrino mechanism. You need to have asymmetric neutrino emission to get the kick, because it's not going to happen from ejecta. I'm fine with saying that some black holes get kicks. There's at least one black hole that we look at the binary system, and it's moving, it has a proper motion, so the whole system got moved, and that kick had to be at least 150 kilometers per second. That's just one. I can explain one. But if it is the whole population, then you're pushing me to believing that neutrinos can drive kicks. Now, if you go talk to the neutrino people, they say, oh yes, that's perfect. Sterile neutrinos, we knew it had to be there anyway. And so at least on the particle physics side, they aren't bothered by it. But we mundane astronomers.
But so this asymmetric neutrino emission is not sterile neutrinos. It's just
It doesn't have to be, but sterile neutrinos are one of the big mechanisms. So there's several mechanisms. Sterile neutrinos is one of them. We may be pushed that way. If the black hole systems still need these kicks, and we've been looking at the black hole systems in more detail, and it's still consistent with them having these large kicks. If that remains, then I think we're going to have to look at kick mechanisms that are neutrino driven, which means that the neutrinos have to be asymmetric, which means that there's more, there's features in the simulations that we're not getting right. And that goes back to the nuclear equation of state. If that's true, then I'm not even doing the core right yet. So we have some work there. Lucas?
Oh, just a comment on the evidence from NuSTAR.
Yeah.
There are also optical observations out of light echoes from Armin Rest that show that Cas-A was asymmetric.
Yeah.
So that's another
And the issue we're trying to see there is it asymmetric? Is it bipolar, or is it something else? Because if it's bipolar, then we can have a lot of engines, and I expect we should have lots of supernovae that are just bipolar. And they would be, superluminous supernova. I'm hoping that they're explained by something other than the standard supernova engine. Magnetic fields are strong, high rotation rates, something like that. So the question is, can we see the difference between a bipolar explosion versus something that's kind of low mode convection? 87A to me seems to fit better with a single lobe going out, not a jet, not a bipolar jet. And so, so it has a single strong lobe. But these are the kinds of asymmetries we're looking at. And you see them, you see them both in light echoes, but you also see them in a lot of the remnants just looking at the Chandra observations. But making sure you believe it is the hard part. Making sure you aren't getting fooled by, in the case of Cas A, the environment was probably also asymmetric, so it looked like it had an asymmetry in the explosion that really was just in the surrounding medium. So that's the difficulty of trying to, at some point you need several pieces of evidence before you start believing it.
So your convective engine, I mean, to my understanding, it appears that that is decoupled more or less from the kick.
It's the way that people have been getting it with the convective engine is they get low mode. So what I didn't talk about is most of these convective engine models, if you run them, you end up going to the lowest mode you can. Most of the energy is in the lowest mode. And so the convective engine produces a kick in that it goes to low mode convection. And Mark Arant first pointed this out in 1995. But if you go look at Thomas Janka's or Tony Metsukapa's calculations, this is how they're getting kicks. It's by going to low mode convection and then having that low mode drive the kick. So the convective engine, its kick it predicts is based on this going to low mode low mode convection when you do the full models. And so that's, if you go look at people's papers on studying kicks, that's how they eject a kick mechanisms.
But then low mode must be quite simple.
Yeah, and so if you look at a lot of the simulations, it gets pretty, I'm worried that you take too much out of the simulations because we're not resolved yet. So one of the biggest issues with our engine models is that we are not resolving this turbulence. But if you look at a lot of the turbulence models, you will see that it goes down to, and there is some belief that this is what it should do. If you have a convective region here, most of the energy is going to go into convective modes that are as big as they can possibly get and still do a convective mode. So you imagine things like, low 3 or less modes. And then there's this, one of the features of the standing accretion shock instability, this vertical acoustic instability, is that it sloshes back and forth. Although they don't see it as much in 3D as they did in 2D, go figure. But this sloshing produced almost a single lobe of convection going out. So this is
dipole. I mean, what's the lowest?
This is a 1. So you can't have it just go. In fact, this isn't a star, but this is an example. This simulation by Woodward and Berwick studying the star is exactly this. This thing is right now doing this. It's sloshing back and forth. So this high stuff peaks here, and then it sends it back out and goes back here. So I had a movie, you would see it sloshing back and forth.
And that was 3D.
This was 3D, yeah.
So in the end, the ejector, it will still predict something like a strong bipolar model, bipolar thing.
So this thing might produce a single lobe. I think that's for the lowest mode that people get, and generally they get this only in a. So this would be a single lobe going out, and this is only in 2D that I've seen it. Although this one's 3D, but only in the core collapse engine. This is in a shell, but in core collapse engines, I've only seen it in 2D models. In the 3D models, they look a little bit more. They look more like this, where you have 1, 2, 3, 4, 5, or 3 kind of upflows and downflows. Although convection can alter this. Convection can make a bipolar thing, but rotation. Rotation can make it more bipolar. But if it's not rotating and you don't have this standing accretion shock instability, you'll get more like 4 or 5 lobes, 3 to 5 lobes of outbursts coming out.
Yeah, one last question was about the progenitor to remnant mass relation. It looks like when if you have this direct fall in, most of the mass ends up in the black hole.
Yeah.
Okay, certainly around 20 solar masses. Then as you get a higher mass stars, you can start to get some more out. that one of the plots? you
Yeah,
showed?
that was this. This
And
was.
what I was going to ask you about this maybe outside your comfort zone is, for things like, certainly there's a problem in the sense that, these first stars are supposed to take out a whole bunch of metals. They're
Yeah.
not first stars, right? But they'd be
Well-
over 100 solar masses or something.
Yeah, and so there's a different way, so first of
Right.
all, if you go more massive, if you're going to the first stars, if you get up to 130 solar masses,
Right, like stuff fall
you can do the apparent stability supernova.
Oh,
So
yeah, sure.
that's one way to get the metals. That has a very specific signature.
Yeah, yeah.
My suspicion is that so we now also know that the first stars are not all 100 solar mass stars. You can get a lot of 20 solar mass stars
Yeah.
too. So
then
these
how
are
do
not
you-
going to inject that much metal. So these stars just
Right.
won't. You can do a strong asymmetry and maybe get some metals out, but I think my guess is your metals are coming from here or from those parastable supernova.
Okay.
And the question is, can we get the right yields from that?
Yeah.
We've looked into this. The subject of getting detailed yields is still a rough one, and you don't even know the IMF that these. We thought we knew the IMF, and this is when we also thought that the first stars were all single stars, and I think now, that was the old ENSO results. They fixed the ENSO code, and now they're getting lots of multiple
Binaries.
systems. Yeah. So who? I don't even know the mass distribution, but. I think if you're 100, if you get into the parent stable range, you can get lots of metals, and otherwise you're limited to, I think, these in the end. I think there's gonna, we even have a 10,000 solar mass star that we've collapsed, and it does not eject any metals.
Does not, sure.
It just
That would
makes
have
a
to be
big black hole.
Okay.
So a 10,000 solar mass star will produce a, nearly
Black hole.
10,000 solar mass black hole.
Any other questions? Okay, if not, Chris is visiting us the rest of the day.